Good morning, good afternoon, or good evening. In this video, we're going to work on Chapter 1, Section 5, Infinite Limits from the Calculus book. Two bullet points here. One, we're going to determine infinite limits coming in from the left side or the right side. And we can also find and sketch the vertical asymptote of the graph of a function. So here it starts out, it says consider this function. Our function f of x is 3 divided by quantity x minus 2. Remember, we're always concerned about division by 0, and here what would zero out this denominator, the x minus 2, would be positive 2. So positive 2 is our vertical asymptote, and we want to figure out what the function does or how it behaves as we approach this naughty number 2. So here, in the earlier section, we've done this graphically and numerically. So here, let's go to the table first and do it numerically. If we type the function 3 over x minus 2 into a TI-89 calculator and we go to the y editor, we put in this x value 1.5 and we get a negative 6. Let's get closer to 2, 1.9. Now our y value jumps quite a bit to negative 30. Now, if 1.9 is close, let's get closer at 1.99. This y value is negative 300. Notice they're all negative and getting bigger, more negative. And then if we add another 9 in there, 1.999, we get negative 3,000. So if we look at the pattern, if we do another 9 on there, 1.9999, the y value should be 30,000. So here, if I erase this little bit, in these red arrows, it says as x approaches 2 from the left. So here's 2, the naughty number. We're approaching from the left, and our outputs, negative 6, negative 30, negative 300, negative 3,000, they are decreasing without boundary. They're decreasing very, very quickly. If we hop to the other side of 2 and we approach 2 from the right side, from numbers above, if we put 2.5 in our calculator, we get out positive 6. 2.1, that would be 3 over 2.1 minus 2, gives us an output of positive 30. Tuck a 0 in there, 2.01, we are at positive 300. Squeeze another 0 in there between the decimal and the 1, and we get output 3,000. Very similar to the left side, but here they're all positive. So we can say the function behaves like this. It increases without boundary as we approach that 2. And then the symbols positive infinity and negative infinity, referred to positive and negative infinity respectively. These symbols do not represent real numbers. They are convenient symbols used to describe unbounded conditions more concisely. Infinity is not a number. You're never going to get there. It says a limit at which f of x increases or decreases without bound as we approach that number c is called an infinite limit. And remember, it's one of the reasons a limit does not exist, due to infinite behavior. So here in example 1, let me back up, I forgot something here. We were supposed to look at this one numerically and graphically, so here was the numeric part. We saw on a table of values what happens as we approach. Graphically, we did identify, the 3 over x minus 2, set your denominator equal to 0, and you get the vertical asymptote will appear here at 2. And then remember, you can never touch or cross a vertical asymptote. So as we're approaching here from the left, we either have to go up or down to positive or negative infinity. In this case, we went down to negative infinity. As we come in from the numbers above 2, again, we only had 2 options, up or down. In this case, the function took us up to positive infinity. So graphically, it's real easy. Just find the naughty number. Here it's 2, and figure out as you're approaching from the left, do you go positive or negative infinity? Same thing from the other side. Be sure you see that the equal sign in a statement like this, the limit of f of x equals infinity, does not mean the limit exists. On the contrary, it tells us the limit fails to exist by denoting the unbounded behavior of the function. Now here in example 1, they just ask it for purely from the graph. Determine the limit of each function as x approaches 1 from the left and the right. So let me move this up here a little bit. Now here on the first one, letter A, our naughty number is 1, and as we're approaching here from the left, I'll use blue ink. The function's going up, up, up to infinity. So we could write the limit as x approaches 1 from the left of f of x. I'm not going to rewrite the whole function. It's right here. That limit is equal to positive infinity. And then red ink from the other side, we're coming in this way. We're going up, 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 also to positive infinity. So we could write the limit as x approaches 1 from the right of the function f of x. That is also equal to positive infinity. Notice it's the same from the left and the right. So we could write, in this case, an overall limit. We could just write the limit as x approaches 1, neither from the left nor the right, from either side, it doesn't matter, of f of x is equal to positive infinity. Now, the combining them here that I did in this black ink, that's not going to be able to be done here in part B. If I move over here, part B, we've got our asymptote at 1. And then let me move it over. I got a little more room if I move it here. Red ink here on the left. So we're coming in here toward positive 1, and our graph is taking us up to infinity. So the limit as x approaches 1 from the left of our function is equal to positive infinity. But if we're coming here from the other side, we're going down, down, down to negative infinity. So our limit as x approached 1 from the right of f of x is equal to negative infinity. Now, since our left and right behavior is different, we could not write this as a single limit. We'll have to keep it as two separate ones. And here it says, numerical solution. I'm going to show you something else. These problems, as you approach an asymptote, like I said before, you either must go up or down to positive or negative infinity. You can't touch or cross them. So here in the first one, letter A, we had 1 over x minus 1 quantity squared. Notice that the numerator of this function is just a constant. It is a positive constant. Down in the denominator, something might happen in the parenthesis, which turns out to be a negative, but we're going to square that negative away. So in this case, our denominator is always positive. Numerator is always positive. Denominator is always positive. That means you're going to head to positive infinity. A positive numerator divided by a positive denominator is a positive result or answer. That means our infinite behavior will be up to positive infinity. Now this one here, we're going to have to do a little more work to figure it out. This function here in the box, our numerator is negative 1 over x minus 1. And let me move this over here. Numerator negative 1 over x minus 1. So let's say we want to approach from the left. We want to come in from a number a little bit less than 1. Mentally I would do 0.9. So this x right here is going to become a 0.99 minus 1. That is a negative denominator. The numerator is negative 1. By default, it's always negative. Negative divided by negative is a positive answer. So as we're coming in from the left, we're heading here up to positive infinity, which we already figured out just by looking at the graph. Let's change that and come in from the right. Maybe we're coming in from the right, so our numbers are going to be a little bit bigger than 1. I would think 1.1. So again, our numerator, the numerator is a negative 1, but our denominator is going to be 1.1 minus 1. Again, when we come in from the left, we pick a number a little bit under 1. Here we're coming in from the right. We're coming in from the right side, so we pick a number a little bit bigger than 1. So we have a negative numerator. Our denominator when we subtract is positive. A negative divided by a positive is negative. So that means we're heading for negative infinity. Again, with these, it all comes down to the sign of the numerators and the denominators. And numerically, we could have also, just like we did in example 1, put these functions into the TI-89 and come up with a table of values. Vertical asymptotes. The book says if it were possible to extend the graphs in figure 1.40 toward positive and negative infinity, then you would see each graph becomes arbitrarily close or infinitely close to the vertical line x equals 1. This line is a vertical asymptote of the graph. We'll study other types of asymptotes in the next section. So here in our box, the definition box, definition of a vertical asymptote, if our function f of x approaches infinity or negative infinity as x gets closer to this number c from the left or the right, then this line at x equals c is a vertical asymptote of the graph. In example 1, note that each of the functions is a quotient. It's in the form of a fraction. And that the vertical asymptote occurs at which the denominator is zeroed out. And the numerator is non-zero. And this next theorem generalizes that observation. But what do we got over here? Connecting concepts. If the graph of a function f has a vertical asymptote at x equals c, then it will not be continuous. We can't draw a line through it. We can never cross an asymptote, so the graph is not continuous at that point. So now here's our theorem, the theorem of vertical asymptotes. And it starts by saying let two functions, f and g, be continuous functions on some open interval containing point c. If f of c is not equal to 0. So what this is saying is the numerator here is not equal to 0. And g of c is equal to 0. So that means our denominator is equal to 0. And there exists an open interval containing c such that g of x is not equal to 0 for all points not c in that interval. Then the graph of the function, they're just calling the divided function h of x, f of x over g of x, that function will have a vertical asymptote at that c value. Again, math theorems, especially in calc, could be very wordy. They want to make sure they cover all the bases, dot all the I's, and cross all the T's. The vertical asymptote theorem boils down to this. If you have a number in your numerator, any number, positive or negative, and your denominator is 0, you have a vertical asymptote at that x value. Number up top, 0 downstairs, there's a vertical asymptote. And an example 2 here. They want us to find some vertical asymptotes. So here, I don't know why the book set it up like this. When x equals -1, the denominator of this, let's just, an easier way to do it if they didn't give us that setup. When you're looking at a fraction, you want to look at just the denominator and say when the denominator is equal to 0, I'm going to have trouble. So here we're going to solve for x. We would divide by 2. 0 divided by 2 is 0. So we have x plus 1 is still equal to 0. Subtract 1 from each side. X equals -1. That is going to be where we run into a vertical asymptote for that fraction or that function. Again, because the numerator is a number and our denominator would 0 out. Let's see what this says. There it is. Ooh, no, hold on. What are they? Okay, I was checking to see if they said, and come up with the graph, but they didn't ask that. But we did find the vertical asymptote. Here at -1, we would have that VA. If we picked a number to the right of it, let's even go as far as 0. If we put in a 0 for x, our numerator is positive, our denominator is positive. So as we're coming in from that side, we are going to be heading to positive infinity. But if I picked a number like -2, I usually like to stay a little bit closer, like -1.1. But either way, when you put it in there, you're going to get a positive numerator and a negative denominator. And that tells us we're heading down to negative infinity. But again, they were only asking for where's the vertical asymptote, and I sort of took that a little far. B. So here, we could either set the denominator equal to 0 right now, or they kind of give us this little push in a different direction by factoring the denominator. Our numerator is a square of sums. That will not factor. But we could factor our denominator into an x minus 1 and an x plus 1 term. And then we could set each of those to 0. This one will 0 out at x is 1. The other one will 0 out at -1. So here we're going to have two vertical asymptotes. Our numerator is always going to be positive. If you square something, it's always positive, and then we're going to add a little bit more. So the numerator is always going to be positive, but depending on what x values we pick for our denominator, it might be positive or negative. And an alternate way to find that, if we just took the x squared minus 1 and set that equal to 0, we would add 1 to both sides. The only possible problem here is when you square root both sides, it's real easy to forget the plus and minus 1 on the other side. When we factored it, we didn't run into that. So here we're going to have a pair of vertical asymptotes when we check out the graph. And there they are, vertical asymptotes at 1 and negative 1. In between those asymptotes, we have a downward opening parabola and kind of an L here in quadrant 1 and a backward L in quadrant 2. When we can see here from the graph, as we approach this negative 1 from the left, we're heading to positive infinity. As we approach positive 1 from the right, we're also heading to positive infinity. And here's where our approaches head to negative infinity. When we're approaching this negative 1 from the right or positive 1 from the left, the graph is heading down. We're stuck in between those asymptotes. There's B. Now this one is a little different. By writing the cotangent function in the form of. Now I would always think, if you, hopefully you remember the graph from pre-calc of what cotan looks like, but we could, rewrite it in another form. Remember, tangent, if we have tan, that's sine over cos. So cotan is just the flip. That would be cos x. That's supposed to be an s. That looks like a 5 now. Cos of x divided by sine x. Divided by sine x. So again, the directions say, I believe it's determine where all the vertical asymptotes are going to lie. So now if you remember what the sine graph looks like from pre-calc, remember we would start on the origin, we would end at 2 pi, and sine would cross in the middle. So it would look like this. So every time our denominator sine is equal to 0, we're going to have a vertical asymptote. The first one occurs at 0, the next one's at pi, and then at 2 pi. So these are going to occur frequently. We could write it as the set of all x, such that if we're asking us where they are, that would be where x is equal to some number n times pi. Here would be 0 pi, 1 pi, 2 pi, and that would keep going on, 3 pi, 4 pi, and even negative numbers. We could make that n value negatives and it would still work. And to reinforce that, I hope you remember the graph of cotan from pre-calc, because it is the easiest one in my opinion, one of my favorites. Here's our xy axis. Remember, cotan's first asymptote is always on the y-axis, and then it is a 1 pi jump in any direction to the next asymptote. So the next one would be at pi, and then we'd have another at 2 pi. And again, this is just where the graph of the sine wave crosses. If the sine wave is crossing there, cotan is going to have a vertical asymptote. And let's bring out the book's graph. I'm sure it's better than mine. Oops. There it is. There's our cotan. Oh, and I forgot to actually draw the cotan graph in there. So as we approach here, let's just pick this interval. As we're approaching 0 from the right, we're headed up to positive infinity. But as we approach 0 from the left, we're over here heading down to negative infinity. So anytime you pick an asymptote, you will have one up and one down when you're dealing with cotan. And that's the end of that one. Okay. Here. Theorem 1.14 requires the value of the numerator at that value to be non-zero. When both the numerator and denominator are 0 at that point, we obtain the indeterminate form of 0 divided by 0. And we cannot determine the limit behavior at that point without further investigation. So let's see what we got here. Determine all vertical asymptotes of this graph. So if we look at our denominator, we can either set that denominator equal to 0, and we'd get x squared equals 4. And if you square root, you'll get x equals plus or minus 2. So you might think that we have two vertical asymptotes. There's two numbers that will zero out our denominator. But remember, to have a vertical asymptote, the numerator must also be non-zero at that same point. So let's investigate this function here. I already mentioned we could factor the denominator. So if we factor that into an x plus 2 and x minus 2, that might give us clues to help us factor the numerator. And if we break that down, let's see, the factors of multiply to negative 8, add up to 2. That's positive 4 and negative 2. Positive 4 and negative 2. That gives us 2 in the middle and negative 8 at the end. Yeah, there it is. So when we look at it now, we know that we have discontinuities when our denominator is equal to 0. That discontinuity could either be removable or non-removable. If we notice here, we have an x minus 2 factor. Those will cancel. So x equals 2 is a discontinuity. It is a discontinuity on the graph. But in this case, it is a removable discontinuity. Removable discontinuity. When we factored and canceled, the discontinuity disappeared. And we can double check now if we plug 2 into the, well, let's skip that. Maybe we'll come back to that at the end. But over here now, we've still got this part here that was not canceled. If we set this denominator equal to 0, let me get a little more room here. Move this up. So at this other one, let me rewrite it. We've got x plus 4 left in the numerator, x plus 2 downstairs. So now where this is going to equal 0, at x equals negative 2, if we put negative 2 in the numerator, that's also going to give us a positive 2. So this will be a vertical asymptote. It's not removable. We cannot cancel it. So x equals negative 2 is also a discontinuity, but it is non-removable. It's a non-removable asymptote. There we go. So there will be homework questions, and I'm sure on the test, I will have a question similar to this, and it will say identify the discontinuities, identify if they're removable or not. Here we factored and canceled, we removed the discontinuity. So what does this do to the graph? We know that at negative 2, we had a non-removable. So that's definitely going to be a vertical asymptote. But what was going on at positive 2, we have a discontinuity in the original function, but it's just a little hole in the graph. When we factored and we canceled, we paved over that pothole. It disappeared. And that was not the case in the remaining part. We could not factor and cancel. We were stuck with that vertical asymptote. Up next, example 4. Find each limit. Now let's see here. Let's go back to remember when I said this is all about signs. Is it positive or negative as we get close to that number? So in this one, we're approaching positive 1 a little bit from the left. So I'm thinking 0.9. So my numerator here, x squared, will be 0.9 squared minus 3 times 0.9. Denominator is x minus 1, or that'll just be 0.9 minus 1. So if we work the math here, 0.9 squared, I'm just going to work down here. 0.9 times 0.9 is 0.81 minus, we got 3 times 0.9, that's 2.7. 2.7. Down in the denominator, we just still have just that 0.9 minus 1. So we're not really worried about what the number is, just the value. If you have 0.8 and you minus 2, your numerator's negative. Downstairs, 0.9 minus 1 is also negative. Negative divided by negative is positive. So this limit is heading, it does not exist, and we're heading to positive infinity. We're approaching again just from this one side. If we check the other side, it might be something different, and that's what we're going to do here in the next part here. So again, we're coming in from the left, in this case, positive infinity. So now we're coming in at 1 from the right, or a number a little bit bigger than 1. So I'm going to think 1.1. This is going to be 1. What is wrong with this thing? 1, there we go, 1.1 squared minus 3 times 1.1. That's supposed to be a 3. Down in the denominator will be 1.1 minus 1. So up in this numerator, 1.1 squared is 1.21 minus 3 times that is 3.3. Denominator 1.1 minus 1. So here our numerator is negative. I think we saw that on the other side. But now our denominator is positive. A negative numerator divided by a positive denominator is a negative overall answer. So that means as we approach from the other side, we're heading to negative infinity. The limit fails to exist. Infinite or unbounded behavior. In this case, it's to negative infinity. Here's the graph. If you type that into a TI-89, it's kind of hard to see here. The vertical asymptote would be right here. But as we came in from the left, or 0.9, heading up to positive infinity, as we came in from the other side, heading down, down, down to negative infinity. And I think that was all for that one. Yeah, just find the limit. I think I made these up, and that might have been a warm-up from a previous year, so let's skip by that. The technology pitfall: when you're using a graphing utility, be careful to interpret the graph correctly of any function with a vertical asymptote. Some function or graphing utilities have difficulty drawing that type of graph, and the TI-89 is no exception. So time for some more properties. Some of these might seem similar. These properties do kind of echo through the class. So to set this up, it's the properties of infinite limits. We've done properties of limits. Now it's for infinite limits. So here it says, let C and L be real numbers. C is some value on the x-axis that we're going to approach. L is a number on the y-axis. It's a limit. It's a real number. Two functions, f and g. So here, function f, as we approach C, has a limit to infinity. Function g has some number, like 7 or 10 or 15. It doesn't matter. It is just a real number. It's not infinite. So here, if we have the sum or difference, if we're going to add infinity plus or minus some finite number, that's going to be infinity. Think about infinity plus 1. Well, that's just infinity. Or even infinity minus 10,000 is still infinity. If you take infinity and add or even subtract some finite number, the result is always going to be infinite. The next one here deals with multiplication. So remember, L is a number. If L is positive, a positive number times infinity, remember f of x is equal to infinity, so this just says if you have a positive number times infinity, it's equal to positive infinity. And if L is negative, you have a negative number times infinity. Well, negative times positive is negative, so that changes it to negative infinity. Those properties of multiplication by positives and negatives, they're not hurt by infinite limits. And we got this quotient rule here, or the quotient property of this. The numerator here is a finite number. Remember this, that limit of g of x is equal to L, a number like 10 or 20. Down here, our denominator f is infinitely big. Let me write it again down here. If you just have any number divided by infinity, that's heading for 0. Because think about it, if we just make our denominators bigger and bigger, 1/10 is small, 1/100th is smaller. If I make my denominator bigger by adding another 0, the overall fraction is smaller. So if we have a finite numerator like 1, or this could even be 2 or 10 or whatever, but as that denominator grows infinitely big, that is heading for 0. Similar properties also hold for one-sided limits and for functions for which the as we approach heads for negative infinity. So there's our properties. Again, very similar to properties we've seen already. Let's see here. What are they asking for? Because the limit as we approach 0 of 1 is equal to 1. And as we approach 0 of 1 over x squared is equal to positive infinity, we're just sort of applying these properties. So this, when we look at it as a limit, this becomes 1 plus infinity. 1 plus infinity is equal to infinity. That is property 1 from the last theorem. And here we're approaching this 1 from the left. We have our x squared plus 1. That limit we could direct sub and get a 2. And we have here we're approaching 1 from the left of this cotan of pi times x. That's equal to negative infinity. We're approaching an asymptote. So notice here it's in the form of a fraction. So our numerator, the x squared plus 1 part, that's just equal to 2. And our denominator, as we approach that asymptote, we were told we're heading for negative infinity. Remember, if your numerator is just a number and your denominator is either infinite or negative infinite, that's heading for 0. That becomes a very small fraction and it heads to 0. Letter C. The limit as we approach 0 from the right of 3 is 3. As we approach 0 from the right of natural log x on the graph, that would take us down an asymptote toward negative infinity. Here, we're just multiplying them. The limit as we approach 0, that was our approach number for both. Here, we're just multiplying 3 times natural log. Well, the 3 part, that has a limit of positive 3, and we're going to multiply it by the natural log answer, negative infinity. 3 times negative infinity is equal to negative infinity. Now this, I'm looking at my note packet. My note packet's old from an older edition of the book. This part D here, hopefully it's in your notes. It's, like I said, it's not in mine. Let's work through it here. We're approaching 0 from the left of x squared. That's equal to 0. We could direct sub that. As we approach 0 from the left of 1 over x, that's equal to negative infinity as we approach an asymptote. Let's see here. So we're approaching, here's our x squared part. That's equal to 0. And then we're going to add to that the limit as we approach this. That's negative infinity. 0 plus negative infinity is equal to negative infinity. Property 1 of that same last theorem. Let's see here. What's this graph down there? I think that's just talking about the natural log component that we talked about in there. With a graphing utility, you can confirm the natural log function has a vertical asymptote at 0. And if you remember graphing natural log from pre-calc, remember the basic exponential. Any exponential is going to go through this point, going up, up, up. The natural log graph goes through the reflected point there, and it looks like this. We're heading up toward infinity this way. But as we approach the y-axis, that's a vertical asymptote heading down. Another really good thing this pays off in the long one. Remember that the natural log of 1 is equal to 0. That pops up quite a bit throughout the class. This is our natural log graph here, and when we're here on the x-axis at positive 1, we're crossing the x-axis, so our value on the y-axis would be 0. Natural log of 1 is 0 is a biggie. Memorize that. That helps a lot. Don't pay any attention to this. The homework assignment will be provided on Microsoft Teams, or I'll just give it to you in class. I hope you enjoyed the video.